This machine, the one that looks like a golden chandelier, keeps showing up in the news. Some say it can finish in 1 second what a supercomputer couldn't crack in 10,000 years. Some say it's about to break every bank's encryption on Earth. And some say it can simulate an entire universe. Among these claims, some are true, some are wildly overhyped, and some are really just philosophy. This video won't hype it up and won't pour cold water on it either. It'll do just one thing: hand you an honest ruler. This ruler has 3 layers: what's already been proven, what's still frontier and unsettled, and what's pure hype. As we explain what quantum computing actually is, we'll keep sorting each claim into these 3 layers. First, let's be clear, this is not distant science fiction. Google, IBM, and research teams in China have all built quantum computers that genuinely run. Some you can even reach through the cloud. They are real machines. They're just still a distance away from changing your daily life. And mapping that distance is what today is about. Let's start with how your phone and computer work. In a classical computer, the smallest unit of information is the bit, and it's only ever one of 2 states, 0 or 1. Essentially, it's countless tiny switches. On means 1, off means 0. A quantum computer uses the qubit. And here's its most counterintuitive feature. Before you look at it, it doesn't have to be just 0 or just 1. It can carry a bit of 0 and a bit of 1 at the same time. This state is called superposition. A common analogy is a spinning coin. While it's spinning fast on the table, is it heads or tails? Neither, really. It's in an in-between, blended state. Only when it falls and you look does it become one definite face. Here's a crucial point that's easy to miss. Superposition is not we don't know whether it's 0 or 1. It genuinely is both at once until it's measured. The act of measuring forces it to pick a side and gives a random, definite result. It sounds strange, but that's the source of all its power and all its trouble. Mathematically, a qubit is written like this: alpha times 0 plus beta times 1. Alpha and beta set the probability of getting 0 or 1 when you measure. Draw out all the possible states and you get this sphere, the block sphere, where every qubit is a single point on the surface. This is the only formula in the whole video, and it's totally fine if it doesn't stick. Now let's take apart the first and biggest misconception. You've surely heard it. Because of superposition, a quantum computer can try all the answers at the same time, and that's why it's unbelievably fast. That's half right and half wrong. It's true that 30 qubits in superposition can carry over 1 billion possibilities at once. 300 qubits carry more states than there are atoms in the observable universe. Sounds unbeatable. But here's the catch. The moment you measure, all those possibilities instantly, randomly collapse into just 1. You can't read out 1 billion answers at once. You get exactly 1, and most likely it's a useless random number. So the real trick of quantum computing isn't computing a lot. It's something called interference. Picture throwing many stones into water at once. Where crest meets crest, the wave climbs higher, and where crest meets trough, they cancel out. The entire art of a quantum algorithm is to shape these waves so the possibilities pointing to wrong answers cancel to 0, while the ones pointing to the right answer add up and amplify. When you finally measure, the correct answer pops out with very high probability. Here's a picture. Say you're searching 10 million drawers for one key. The classical way is to pull them open one by one. Interference lets the echoes from all the empty drawers cancel each other out, while the signal from the right drawer grows stronger and surfaces, so you need far fewer tries. That's the intuition behind the famous Grover search algorithm. Remember, just this one line: the power comes from interference, not from parallelism. A quantum computer that can't use interference is no smarter than your phone. And this one is solidly proven. There's a second thing that makes qubits more than a pile of spinning coins: entanglement. When 2 qubits become entangled, they're no longer 2 separate individuals. They share one single inseparable state. Measure one of them, and the other, at the very same instant, shows a perfectly matching result, no matter how far apart they are. Einstein was so troubled by this, he called it spooky action at a distance. It's precisely because entanglement binds many qubits into one inseparable whole that interference can act across that vast space of states all at once. Put the other way, without entanglement, a quantum computer collapses back into a bunch of separately spinning coins, and no amount of them creates any advantage. Entanglement isn't a decorative bonus. It's the core resource of nearly every quantum algorithm and error correction scheme. But a splash of cold water, it cannot send information faster than light. The correspondence you see only means something once the two sides compare their results. So, quantum entanglement means instant communication is hype. If quantum computing is so powerful, why isn't there one in your phone yet? Because of one enormous problem. Quantum states are extraordinarily fragile. Superposition and entanglement need the qubit to be completely sealed off from the outside world. But in reality, a little heat, a faint electromagnetic wave, one small vibration, any of these makes it leak to the environment, and the superposition falls apart. This process is called decoherence, and it's been quantum computing's biggest enemy for decades. So back to that golden chandelier from the start. It's actually not the computer itself, but a dilution refrigerator. The real chip sits at the very bottom, cooled to about minus 273 degrees Celsius, just 1/100 of a degree above absolute zero, far colder than outer space. Add ultra-high vacuum and layer upon layer of shielding, all to give the qubits an absolutely quiet home. Even so, today's qubits still err easily, roughly once every 100 to 1,000 operations. The classical chip in your hand has to run 1,000 trillion operations before a single error. That's a gap of more than 10 orders of magnitude. Think about how extreme this is. To solve one problem, we build one of the coldest corners in the entire universe and place a fingernail-sized chip somewhere quieter than deep space. Quantum computing is half mathematics and half engineering pushed to the human limit. So what do? The answer is quantum error correction. The idea is clever. Instead of hoping a single qubit never slips, we group many unreliable physical qubits together and have them jointly encode one stable, error-corrected logical qubit. By constantly measuring a certain check relationship among them, the system can find where an error happened and fix it, without ever directly peeking at or destroying the superposition. The mainstream approach is called the surface code. The price: one usable logical qubit may need dozens to hundreds of physical qubits to support it. So here's a counterintuitive conclusion. More qubits is not automatically better. A machine with 10,000 noisy, error-prone qubits may be less useful than one with a few hundred quiet, precise ones. Ranking machines by raw qubit count alone is misleading. The real finish line is called fault tolerance. Its landmark moment came at the end of 2024. Google's Willow chip became the first to go below threshold. As it scaled up the error correction, the logical error rate didn't rise. It fell, and fell exponentially. That was the first proof that this whole path actually works. A solid, confirmed milestone. How far is that from useful? Take cracking today's bank encryption as a yardstick. A 2019 estimate needed about 20 million error-prone qubits running for 8 hours. By 2025, new methods pushed that down to under a million in under a week. The machine doesn't exist yet, but the bar it requires is dropping at a startling pace. The industry roadmap looks roughly like this. Around 2030, the first machines that reliably beat classical supercomputers on a few specialized tasks. And only later, through the 2030s, a gradual path to broadly useful, fault-tolerant quantum computing. In one line, worth being excited about, but be patient. There's more than one road to building a qubit. Today, 5 main tracks are running side by side, each with its own strengths and weak spots. Superconducting circuits, the route Google and IBM take, have fast gate operations and can borrow mature chip fabrication, but they must sit inside a dilution refrigerator. Trapped ions suspend single atoms in a vacuum with electromagnetic fields, reaching the best fidelity and coherence. And any 2 qubits can connect directly, but scaling up the control system is hard. Neutral atoms use laser tweezers to arrange reconfigurable grids of atoms, highly parallel and near room temperature. Photonics computes directly with light. naturally suited to networking and plugging into optical fiber, but plagued by the loss of light. And the fifth, the topological qubit Microsoft is betting on, is, in theory, inherently resistant to errors at the physical level. Microsoft claimed it had built one in early 2025, but this needs a clear caveat. Reviewers at the top journal Nature concluded the data does not prove it actually exists, and the field is broadly skeptical. So the topological road is frontier and unsettled, even with a touch of hype. The overall picture is a bit like the earliest years of aviation: propellers, jets, and all sorts of odd flying contraptions taking off at once, with no one daring to say which design wins in the end. At the very end of 2025, the trapped ion camp's Quantinuum unveiled a new 98-qubit machine where any two qubits connect directly, pushing this race another step forward. So what is a quantum computer actually good at? Let's start with the most solid one: simulating molecules and materials. Nature itself is quantum. To compute exactly how electrons behave inside a complex molecule, a classical computer hits an exponential explosion. But a quantum computer natively speaks the language of the quantum, so it's a better fit. A classic example is nitrogenase, an enzyme bacteria used to turn nitrogen from the air into fertilizer at ordinary temperature and pressure. Industrial nitrogen fixation, by contrast, still needs high heat and pressure, consuming 1% to 2% of the world's entire energy supply. If a quantum computer could work out how nitrogenase does it, we might design a room temperature catalyst and save a staggering amount of energy. Better batteries, more targeted drugs, they're all the same kind of problem. This is quantum computing's most credible early value. But there's a pile of overpromised directions too: financial portfolio optimization, logistics scheduling, quantum AI. In these areas, classical algorithms are already extremely strong. Most efforts are still pilots, and no one has shown a robust, verified practical advantage yet. Flip it around. There are things that will probably never do better than a classical computer: streaming video, sending messages, spreadsheets, running the apps on your phone. For these, classical chips are fast and cheap. Quantum has no role to play and doesn't need one. Its stage is the problems that are quantum by nature. And one more thing to be clear about: the quantum supremacy you keep hearing, like Google's 2025 quantum echoes, is a real, beautiful result. The machine computed something no classical supercomputer can reproduce. But what it computed was a specially designed physics problem with no practical use. Supremacy is not the same as useful. And a quantum computer won't become your next laptop. It's a coprocessor for specific hard problems, not a do-everything box. Now to the topic that keeps governments up at night: cryptography. Our online banking, our chats, our state secrets, most of them rest on a kind of public key encryption whose security stands on one thing: that factoring a large number back into two primes is something classical computers can't crack. But back in 1994, the mathematician Peter Shor proved that a powerful enough, fault-tolerant quantum computer could, with Shor's algorithm, do that factoring blazingly fast, making this public key encryption fail in an instant. Note: public key. The symmetric encryption you use every day, like AES, stays essentially safe just by lengthening the key. Quantum does not break all encryption. Subtler still is a threat called harvest now, decrypt later. An adversary can, starting today, quietly intercept and store your encrypted data, then come back and unlock all of it once. A powerful enough quantum computer exists. In other words, the threat actually begins today. Why the rush to change the locks now? Because some secrets have a shelf life of decades. A medical record, a business contract, a state secret quietly harvested today still does damage if it's open 20 years from now. That's why post-quantum migration has become a race against the clock. So the whole world is scrambling to swap locks. The U.S. standards body NIST released its first batch of quantum-resistant encryption standards in 2024 and urged everyone to migrate as soon as possible. As for when the machine that can truly break things arrives, experts call it quite possible within 10 years, and likely within 15. No one can promise, but no one dares bet it won't come, which is why the money is pouring in like a tide. By McKinsey's estimate, announced national investments already total around $54 billion. In 2026, the U.S. put about $2 billion into quantum through its CHIPS Act and stood up its first dedicated quantum foundry. China wrote quantum into its national 5-year plan, pursuing superconducting, photonic, and neutral atom routes, and used its MESIS satellite to build quantum communication links spanning more than 10,000 kilometers. Everyone understands, whoever first holds a usable, fault-tolerant quantum computer holds the key to the future's encryption, materials, and computing power. So, before we put away this 3-layer ruler, where do we actually stand? What's been proven is the real deal. Superposition, entanglement, and interference all genuinely exist. Error correction has been shown for the first time to actually work. And quantum computers really have done things classical supercomputers cannot. Frontier and unsettled are most of the most exciting applications, and paths like the topological qubit. And pure hype is it'll break everything, replace everything, do anything, any day now. More honestly, a truly useful, fault-tolerant quantum computer is most likely still many years away. It won't be the do-everything magic box of science fiction. It'll be more like an extremely expensive, special-purpose accelerator built for specific hard problems, but that takes away none of its wonder. We are learning to compute in the universe's deepest language: superposition, entanglement, interference. So next time you see a headline with the word quantum, I hope you'll take out today's ruler and sort it for yourself. Is this real? Is it frontier? Or is it hype?